Hello, everyone. Today I'm excited to share some recent work on conditional independence testing under Model X, and this is joint work with Aditya Ramdas. So our setup is that we have random variables x, y, and z, x and y being univariate and z being potentially high dimensional. And we'd like to test whether x is independent of y after conditioning on z. And we have a sample of n IID draws from this distribution. We're going to assume that we know the distribution of x given z, instead of a more traditional assumption that y given x and z belongs to some sort of a parametric model. So there are several methodologies that have been proposed to test conditional independence under Model X. And I'd like to highlight Model X knockoffs and the conditional randomization test in particular, both of these being proposed by Candes et al. In 2018. In this presentation, I'll focus mainly on the conditional randomization test, so I'll briefly review this methodology. We start out with any test statistic t evaluated on our data, and then we produce a null distribution for t. Instead of using some sort of assumption on y given x and z, instead we're going to build a null distribution by resampling x from its conditional distribution given z. So we repeatedly resample x given z and recompute the test statistic on this resampled data, and then compare the original test statistic to the resulting null distribution. So usually t would be defined via some sort of a statistical machine learning method that tries to learn the distribution of y given x and z. This could be the lasso or it could be anything else. And it's been observed that the performance of this machine learning method impacts the power of the Model X methodology. And so the goal of this talk is to quantify the impact of the test statistic on the power of the CRT. So as a starting point, I'm going to ask, what is the most powerful CRT against the point alternative? And this point alternative will be specified by an alternative marginal distribution for z and an alternative conditional distribution for y given x and z. So we have a null distribution here, which is simply a rewriting of the conditional independence hypothesis, accounting for our knowledge of the distribution of x given z. And then here is the alternative using the specified distributions of z and of y given x and z. Now, this is a hypothesis testing problem with a composite null, so we can't directly deduce what is the most powerful test. However, what's going to make our problem easier is that the conditional randomization test is also a conditionally valid test, which means that if you fix y and z at their observed values, the resulting test viewed as just a function of x is still a valid test. So we can ask what turns out to be an easier question of what is the most powerful conditionally valid test? So viewing y and z as fixed and only viewing x as our random data, we can derive that under the null hypothesis, the distribution of x given y and z, since it does not depend on y, is simply this distribution of x given z that we have assumed that we know. And then under the alternative, we can compute the distribution of x given y and z using Bayes' rule. So the punchline here is that conditioning on y and z has reduced a composite null to a point null. So we arrive at a simple hypothesis testing problem. And so we can read off the most powerful test statistic directly from Neyman-Pearson. So what we get is the ratio of the two likelihoods on the previous slide, which simplifies to this quantity here. And we can actually even throw out the denominator because it's not a function of x, and so it won't change upon resampling. So what we're left with is that the most powerful conditionally valid test rejects for large values of this likelihood of y given x and z under this assumed alternative model. And so it turns out that this test is exactly the conditional randomization test based on this test statistic viewed as a function of x, y, and z. So this leads to this result, which is that the CRT based on this optimal test statistic, it's not only the most powerful conditional randomization test, it's also the most powerful conditionally valid test against this alternative. So this result gives us our first indication of why we may want to use a machine learning method to learn the distribution of y given x and z. It's because we're really kind of under the hood trying to approximate that distribution, which leads to the most powerful test statistic. So this result has connections to lots of known results. For example, if the model for y given x and z happens to be a linear model, then the optimal conditional randomization test is based on this statistic, which is the difference in these residual sums of squares, which is essentially the same as the F statistic from ordinary least squares. Next, there are also connections to unbiased testing, where conditioning on a sufficient statistic for the nuisance parameters also reduces a composite null to a point null and lets you derive an optimal test. And then finally, this is connected to the holdout randomization test, which is a version of the conditional randomization test where we learn f hat of y given x and z on a training data set, and then apply the CRT based on the likelihood from the learned model on the test set. And so in the context of the optimality result on the previous slide, we can reinterpret the HRT as essentially approximating the optimal CRT. Now, of course, we never know the true model for y given x and z, so we must learn it. And so in the second part of my talk, I'll address the question, how does our error in learning that distribution impact the power of the conditional randomization test? So to consider a concrete case, let's say that y depends on x linearly and on z non-parametrically through this arbitrary function g. And let's say that we have an estimate g hat of g. Assume that we've trained it on a separate data set that we keep fixed throughout. Now, how does the error in g hat impact the power of the CRT based on g hat? So in particular, let's consider the CRT based on this test statistic t, which amount to a correlation between x and y after accounting for z in both of them. So we adjust for z, we just x for z by just subtracting the conditional expectation of x given z, which is known based on the model x assumption. And then we adjust y for z by using g hat, which we've estimated. Now, for simplicity, let's assume that the variance of x given z is always a constant s squared independently of z, and define the test error script e as the expected square difference between g hat and g. Now, let's consider an asymptotic regime where we consider a fixed dimension as well as keeping our training set fixed. And let's let the sample size go to infinity, and let's consider a local alternative for the effect size beta. The result we get is that the power of the CRT against these local alternatives converges to this simple expression here, and we can directly read off what are the impacts of the various problem parameters on the power of the CRT. And so the part that interests us in particular is this denominator here, where we see that the power that a larger prediction error in g hat diminishes the power of the CRT essentially by inflating this denominator here. In other words, we see the error in g hat directly adding to the irreducible error in the regression formula. So again, this result seems pretty familiar, and in fact, this is very similar to what you would get if you did a local asymptotic power analysis of standard linear regression. So to make this a little bit more precise, let's consider the linear regression problem you obtain by subtracting g hat out of both sides of the assumed semi-parametric model. So now we're regressing y minus g hat of z on x. And there's this new noise term epsilon prime here, which has this variance. And the test statistic that we've chosen is basically an unnormalized version of the ordinary least squares t-statistic. And so the null distribution of this t-statistic, if we're working under the least squares model and conditioning on x and z, turns out to be this normal distribution with this particular variance. And so perhaps a surprising observation is that the resampling distribution of the conditional randomization test, where now instead we're conditioning on y and z instead of on x and z, converges to the exact same limit. So what this means is that under that semi-parametric alternative, the CRT resampling distribution is actually equivalent to the OLS null distribution, corresponding to a least squares model with this particular variance. So, so this gives us some more intuition about the power formula that we saw on the previous slide. Now, there are many directions open for future work. For example, Model X methods in conditioning on the response Y, are they limiting themselves in any way? And is it useful to consider other kinds of tests that are not conditionally valid? Next, is it possible to go beyond point alternatives in our finite sample optimality results? And finally, it would be very important, I think, to extend such results to high dimensions. And in particular, such results are already starting to become available, at least in the special case where we're using the lasso as a test statistic. So to conclude, thinking about these kinds of questions can improve our understanding of Model X methodologies and hopefully can help guide their development in the future as well. So that's all I have. And if you'd like to learn more, please check out our preprint, which is available on arXiv. Thank you.